Hi, good morning, everyone. My name is Raghu Kumar. I work as a Thank you. Yep, I just want to provide an introduction to the group and an MPAS very briefly. And I want to provide how NVIDIA is looking at using GPUs for MPAS. But the actual talk about the implementation, the latest results, the methodology, the strategy for porting is provided tomorrow by Supreet on this talk, MPAS on GPUs at 11:40. So that would be actually the presentation if you really want to dwell into the entire model development on what it is. I just want to touch upon what we are planning to do from NVIDIA's side for MPAS and what the current status is. So this is the small group of developers that I personally work with, which is basically two software engineers from STP group, which is Supreet and Sina, and one from MCube, which is Michael. We also have support from NVIDIA's side, which is Carl Ponder, Brent, and Nick. From our chunk of coding development comes from University of Wyoming, where we have a number of students, quite a few who are available today here, work on porting this particular model onto the GPUs. Of course, apart from this group, it's a bigger part of the group, but this is the small closed group that I personally work with and who do the heavy lifting to move the code over to the GPUs. For those of you who don't know, MPAS is basically a meteorological model, which is a fully compressible, non-hydrostatic equation written in flux form. It's basically an unstructured Voronoi grid that we are using. It's also having a third-order Runge-Kutta method with fast horizontal waves just subcycled out. But I want to quickly move to what I really want to talk. This was our original MPAS. The project originally, when it started from NCAR a few years ago, NVIDIA was one of the collaborators. The plan was to take MPAS and look at the number of different modules there and then port most of it onto the GPUs. So I've listed most of the important routines here, which is the die-core, scalar transport, halo exchange, and microphysics, surface layer, boundary layer, convection, gravity wave drag, radiation, land surface models. So the plan was all the green ones that you're seeing there to be ported onto the GPUs, whereas the blue ones that you're looking here are supposed to remain on the CPUs so that you would obtain a full node utilization. Radiation was planned to be lagged so that you could actually give CPUs enough time to finish the radiation. And we also have diagnostics that the CPU would run and some bookkeeping in order to keep all the things checking and moving in the direction. And then on the other side of it, you would see that for the data to be written back onto the netcdf files, you would actually have to move the data from the GPU to the CPU and then write it onto the hard disk, print it as netcdf files, and then use that later for the visualization. However, that idea has now evolved a little more. It's not just about porting, but we're also looking at doing a visualization as well, since the data is already on the GPU. So the idea here is as you run MPAS on a set of HPC nodes on one end, there's an adapter code that creates a pipeline and then streams the data that's already on the GPU to another GPU, which invokes ParaView, and then you can actually look at the visualizations in situ. So that's the overall goal that we're working on at this point. I want to show some of the results that we have from Prometheus perspective, which is at NVIDIA's internal cluster. So for comparison, I'm using IBM Summit supercomputer, which most of you are familiar with. The NVIDIA's Prometheus cluster is basically a DGX1 node, which has about 8 GPUs, 16 GB in memory. The one thing to take away there is it has a 4 IB interconnect per node, which allows it to actually have one IB connection for every 2 GPUs. The third one I'm using for a CPU comparison would be the NCAR Cheyenne supercomputer. So this is a few months old, but it kind of tries to show the point that I'm trying to make. On the y-axis, you see the number of days that I can simulate if we run the MPAS on a given set of nodes for 1 day of execution. So 1 day in real time, if you execute MPAS, how many days can you simulate? That's what I'm trying to show here. So here on the topmost line, you can see the DGX running a 15-kilometer model. And you can see that the last part of the curve is kind of all over the place. That's because we are running out of parallelism at that point, and then there are some unknown effects that, some unexpected behavior that it shows. But right below that is the Summit 15-kilometer. So we are slightly outperforming the Summit here, mainly because MPAS at this point, the code that we have on the OpenACC side is communication bound. And having the 4 interconnects on the node actually helps boost the performance a little more than what Summit can. So below that, you see the red or orangish kind of line where we have the DGX 10-kilometer, closely followed below that by the Summit 10-kilometer. And then we have the 2 lines on the bottom here for the Broadwell's 15 and 10 kilometers. These 2 are basically run right out of the MPAS's trunk code, Intel compiled as released on the trunk. Well, one of the other things I want to point out is that the difference here you can see as we move from the Broadwell node comparison, we are almost getting between 3 and 4 times the number of days that you can simulate when we shift from one curve to another. On the x-axis here, we're looking at a Volta comparison. It's not a DGX node. It's actually a single Volta GPU compared with a single dual socket Broadwell node count. Now, those were basically the die-core results, which has been presented before. We're moving on towards porting the full MPAS. Of course, the full results, as I said, will be provided by Supreet, but I wanted to give what we're looking at on a Prometheus node as of today for physics. It's not, we have taken 4 different physics routines here that we have been able to successfully port and to a certain degree validate very specific test cases. The surface layer, boundary layer, gravity wave drag, and the microphysics. I'm comparing this with a 40,000 points per dual socket Broadwell node, and then providing a speed up on a single V100 node. This is actually created, this run is basically obtained from embedded code, meaning to say it's actually running on the GPU as a whole MPAS. It's not actually a kernel or a small portion of the code. This is actually a production run MPAS that we are picking off these runtimes off. And these actually do include the data transfers that become necessary when we are trying to execute die-core and physics. So on the least side, you can see the surface layer. We're not able to accelerate it by that much. It does have a significant amount of data transfers. It also has a very minimal parallelism we can exploit. But on the other side, we have microphysics, where we have almost no data transfers there, but at the same time, we're also able to exploit the parallelism to the best level possible. The blue ones indicate the current version, and the green ones indicate what we have in the pipeline, which would, if accepted by the MPAS trunk people, then that's what you would expect to see as the speed up. The surface layer, however, in our case, we got lucky that the total execution time of this is actually very, very less than 1% of the total execution time. However, the microphysics takes about 50% of the physics execution time. So overall, we are actually looking at some good numbers, even in physics for MPAS. The current status is we have had some good successful executions on Summit for as far as the MOIS dynamics is concerned. We've been able to run 15, 10, and 5 kilometers on Summit using at least 1,500 volts. The plan is to run about 3 or 2 kilometers resolutions in the next couple of 2 to 4 weeks. at least using 6,000 volts. And if everything goes right at the 2 kilometer, we plan to use about 16,000 volts on the summit to get some performance numbers. Physics, we're currently running physics on the GPUs, but the Natitke, as I did not show those, that's not yet tested well, and the lagged radiation is not yet implemented, and that's what we are working through at this point. And the validation is not a full validation where we have a bunch of different test cases. We have a very select few test cases that we are looking at, and then that's what we're presenting at this point. As far as the in-situ utilization is concerned, we're able to actually achieve this on the CPU at this point. We've not moved the code onto the GPU yet. So if you, I don't know if I can play this, but there we go. Yeah, so here is looking at one of the globes where we are tracking given range of temperature on the globe as the execution happens on the background. This data is currently on the CPU. We are using the OpenACC code, but on the CPU at this point. The plan is over the next 30 days to actually move over to the GPUs and then do this at a higher, finer resolution and a better frequency. So that's my talk. Thank you.